Bismillahirrahmanirrahim. Welcome to the Electrical Engineering channel. In this lecture, I am going to demonstrate special purpose induction motors. The special purpose induction motors include reluctance motor, hysteresis motor, universal motor, and many more. But our discussion will be limited to only these three types of the induction motors. And the first type is called reluctance motor. So in the reluctance motor, the stator is similar to a single phase or a three-phase induction motor having the capability of revolving magnetic field. And it is a squirrel cage induction motor, which is actually an unsymmetrical magnetic construction. So this is a rotor of the reluctance or variable reluctance induction motor, and some tooth are actually removed from the outer periphery of the rotor. So squirrel cage rotor, and it is an unsymmetrical magnetic construction. Some tooth are removed from symmetrical construction so that the overall rotor becomes unsymmetrical, because we see some tooth over here and then some gap, then some tooth, then some gap. So such an unsymmetrical construction is used for the rotor design of the variable reluctance motor. So suppose there are in total 48 slots or 48 tooth of the rotor, and first six tooth are removed, second six tooth are kept, then next six tooth are removed, and then next six tooth are kept, and so on. So 1 to 6, 13 to 18, 25 to 30, and 37 to 42. These are the tooth which are actually cut away. So as a result, we get such a final design of our rotor. So the purpose of having such a design for the rotor of a variable reluctance motor is to have a variable reluctance path for the magnetic field produced in the stator. So four salient poles are obtained, and in this way, rotor offers variable magnetic reluctance to the stator flux. The reluctance varies with the position of the rotor. So if the rotor position is like this, and we have such a direction of the magnetic field lines, now the magnetic field lines will be distorted, and they will be trying, or they will be tending to flow through the least reluctance path. So these magnetic field lines will be diverted towards this teeth, and then they will be diverted towards this teeth, and then they will be directed towards the south pole of the stator. So as a result, this rotor will also offer a magnetic field whose direction will be opposite to that of the stator magnetic field, and due to this induction of the magnetic field in the rotor will be reoriented in the direction of the external magnetic field, and it will be attracted by the external magnetic field of the stator. So the final alignment of the rotor will become like this. So these two salient poles of the rotor will be magnetized in the opposite direction to that of this stator magnetic field, so that these rotor poles will be attracted towards this external magnetic field, and it will be the final orientation of the rotor in response to the stator magnetic field. Now, stator magnetic field is actually revolving, so these rotor poles will be attracted towards this stator magnetic field, and as long as the stator magnetic field is revolving, this rotor will also be revolving in response to the external stator magnetic field. So, as a result, this motor will run at a synchronous speed. So, there will be no slip in the operation of such a motor, and it will be running at the synchronous speed. So when a magnetic material is placed in a magnetic field, a force acts on the material, tending to bring it to the most dense position of the field. So this is called a reluctance torque. The revolving magnetic field exerts reluctance torque on unsymmetrical rotor, tending to align the salient poles axis with the stator magnetic field axis to minimize the magnetic reluctance path. Rotor revolves synchronously; its poles lag behind the stator poles by a certain angle called torque angle. So when this magnetic field is revolving at a synchronous speed, This rotor, which whose poles are also magnetized, will be attracted by this external stator magnetic field, and the phase difference between, or the angular separation between this rotor field and the external field will actually not be equal to zero, because this rotor will be lagging behind the stator magnetic field, and that lagging angle is actually equal to delta. So the torque can be expressed by this expression, which is a function of the torque angle. So T is equal to K times B over F square sine 2 delta. K is the material constant, V is the applied voltage, F is the frequency, and delta is the angle between the stator magnetic field and the rotor magnetic field. So when we want to achieve maximum torque, this angle should be equal to 45 degrees, so that sine 90 will be equal to 1, and we will get the maximum torque. So this is the operating principle and working of a variable reluctance, or simply a reluctance motor. The only problem with this motor is that when this motor is running, there are unequal air gaps between the stator and the rotor, and due to these air gaps, this motor will offer jerks and noise, and there will be air friction when these salient poles will be cutting away the air pockets between the rotor and the stator, and due to this reason there will be jerks in the rotor and there will be noisy operation. So this is one drawback of this motor, but the advantage of this motor is that it will not offer any slip, and whatever is the load at the rotor shaft, it will continue to run at the synchronous speed. So second type of the special purpose motor is called hysteresis motor, and this motor also requires a split phase operation and two windings at starting and the running condition, as we have seen in the single phase induction motors. But there is no centrifugal switch required, and the rotor is smooth chrome steel cylinder having high retentivity, so that hysteresis is high, and rotor poles lag behind the stator poles by an angle alpha. The only difference between this hysteresis motor and the reluctance motor is that the rotor in the hysteresis motor is a smooth chrome steel cylinder. So there will be no unequal separation between the stator and the rotor, and there will be no non-uniform air pockets. So the operation of this hysteresis motor will be free of noise and jerks, and it will provide a smooth operation. And in hysteresis motor, the rotor is made of chrome steel, and this is a material which has very high hysteresis loss, or we can say the retentivity is very high for this magnetic material. Due to this reason, the rotor will become a permanent magnet, and when this rotor is placed in the magnetic field, it will be magnetized, and it will preserve, or it will sustain its magnetic properties, so it will become a permanent magnet. And due to this reason, the permanent magnet of the rotor will be continuously attracted by the external magnetic field. So due to this retentivity or stored magnetic field in the rotor, this motor will continue to run under a revolving magnetic field scenario. So the motor power in this case is equal to the hysteresis loss times 1 minus S over S. Here S is the slip. So this motor always offers a slip, and greater the hysteresis loss in the rotor, greater will be the acquired output power. The torque of the hysteresis motor is equal to 9.55 times mechanical power divided by the synchronous speed. Here we can see that torque is equal to power divided by omega, and omega is equal to 2 pi ns, and ns is rps, but when we are expressing ns in rpm, it will become 2 pi by 60 into ns. So it will become 60 over 2 pi over here, and this 60 over 2 pi is actually equal to 9.55, and all other expressions will be the same. So hysteresis torque of the hysteresis motor depends on the area of hysteresis loop, and it provides extremely quiet operation, no mechanical vibrations, and tape decks, turntables, precision audio equipment are the applications where hysteresis motor can be employed. And last type is called the universal motor. And the universal motor is actually nothing but a DC series motor. And in series motor, we know that the torque is proportional to the product of armature current and the field current. So when we apply a positive voltage, the current will be positive for the armature winding and the field winding. And when the voltage polarity is reversed, the both armature current and the field currents will be reversed and they will become negative. But when these two negative quantities will be multiplied together, the resultant torque will again be positive. So even if it is a positive cycle or the negative cycle of the current or the flux, the torque will be positive, which can be observed in this figure. So if the direction of field current changes, IA also reverses, so the torque direction remains same and motor continues to run in the same direction. So this universal motor is nothing but a DC series motor, and we are actually operating the DC series motor under AC conditions. Under AC conditions, this motor provides smaller efficiency and it will also provide a low power factor, and there will be sparking at the brush and slip ring contacts. So this is the circuit diagram of the DC series motor. Here we have a field winding and this is the armature winding which is connected in series. So this is called universal motor because we can operate this motor for a DC supply as well as an AC supply. So that is all about our today's very short lecture. I hope you have enjoyed the discussion. For watching more similar videos, please stay tuned to this YouTube channel. Until the next lecture, it's goodbye.